The object is quite large, and it's also aligned in its path with the plane of the planets around the sun. So it's quite intriguing. It offers us a gift, a rare gift.
July 1st, 2025. Astronomers spot something tearing into our solar system. A cosmic visitor unlike any before. The first image from the European Space Agency of 3I/Atlas shatters expectations. No tail, a glow pointed at the sun, and a path so precise it shouldn't be random. Scientists scramble for answers, but the truth behind this object could upend everything we know about life beyond Earth. What is 3I/Atlas really doing here? In the search for cosmic visitors, two names set the standard for what astronomers expect from interstellar objects. In October 2017, Pan-STARRS in Hawaii detected one I/Oumuamua, an elongated, tumbling fragment speeding through the solar system on a steep, hyperbolic path. Oumuamua showed no sign of a tail, no coma, and left scientists debating whether it was a fragment of rock, a frozen iceberg, or something altogether stranger. Its trajectory, inclined at over 120 degrees to the ecliptic, made it clear this was not from our neighborhood. Just 2 years later, in August 2019, a different story unfolded. Gennady Borisov, an amateur astronomer in Crimea, discovered 2I/Borisov. This object was unmistakably a comet, with a classic tail and bright coma, outgassing as it neared the sun. Borisov's orbit was also hyperbolic, but its approach was off the ecliptic, arriving at a steep angle, much like its predecessor. The chemistry and activity matched what astronomers expect from comets born far from Earth, confirming its interstellar origin through both path and behavior. The detection of these two objects set a baseline. Interstellar visitors are rare. Oumuamua and Borisov are the only confirmed examples before 2025. Each was tracked by a network of telescopes, with discovery logs and orbital data archived by the Minor Planet Center. Their paths, speeds, and physical features were meticulously catalogued, forming a statistical framework for how outsiders cross the solar system. Hyperbolic velocity, steep approach angles, and for comets, the familiar tail. These became the hallmarks. On July 1st, 2025, the ATLAS survey telescope in Chile flagged a new object. Its motion was fast, its orbit unbound, and its initial designation, A11PL3Z, quickly gave way to a formal name, 3I/Atlas. Pre-discovery images from June confirmed its trajectory, and observatories worldwide turned their attention to this third interstellar arrival. In every way, the expectation was clear: another odd rock, or a comet with a tail, arcing in from deep space on a path all its own. But this time, the story would not follow the script. Early images from the Hubble Space Telescope and ground-based observatories revealed a shape that defied expectations. Instead of the classic cometary tail, 3I/Atlas appeared as a compact, teardrop-shaped glow, its brightest side facing directly toward the sun. Photometric analysis from Hubble's Wide Field Camera 3, using optical long-pass filters, showed no evidence of jets or active outgassing. The standard signature of a comet, volatile ices vaporizing in sunlight, streaming away to form a tail, was missing. Astronomers turned to the data, searching for natural explanations. One possibility: a volatile pore composition, where the surface was already stripped of easy-to-evaporate ices long before entering our solar system. Another: a thick, sun-baked crust of refractory material, trapping any remaining gases beneath a hardened shell. Both scenarios could suppress the usual eruption of gas and dust, leaving only a faint, sunward-facing halo. The orientation of the glow raised further questions. In most comets, the tail points away from the sun, shaped by solar wind and radiation pressure. Here, the brightest region remained fixed on the sunward side, even as the object's position shifted. Some researchers pointed to phase angle effects. The way sunlight scatters off dust and ice at certain viewing angles can create the illusion of a sunward glow, or even an anti-tail. Yet, across multiple observing platforms, the absence of jets or a trailing coma persisted. Careful image processing ruled out artifacts. The star streaks seen in Hubble images came from the telescope tracking the comet's rapid motion, not from any physical feature. No evidence of cosmic ray hits or instrumental ghosts appeared in the processed frames. Every dataset converged on the same conclusion. The tailless, sun-facing glow was real, not a trick of the camera or a quirk of perspective. The lack of a tail, coupled with the persistent sunward brightness, set 3. ESA/ATLAS, apart from both Borisov and the vast majority of known comets. With no jets to measure and no dust plume to model, astronomers faced a puzzle. The next step, mapping the object's trajectory, would only deepen the mystery. 3. ESA/ATLAS does not just break the visual rules of interstellar visitors, it shatters the statistical ones. Its orbit lies almost perfectly along the ecliptic plane, the same flat disk traced by all major planets. The inclination is measured at roughly 175 degrees, making it retrograde, but only about 5 degrees off the solar system's own alignment. For a random interstellar object, simulations show this geometry should occur less than 2 times in 1,000, a probability near 0.2%. Most hyperbolic visitors, like Oumuamua and Borisov, arrive from steep angles, swinging through the solar system on paths that cross the ecliptic only briefly, if at all. The oddity deepens with the object's course through the solar system. After entering, its trajectory threads between planetary orbits, passing close to Mars and then Jupiter in a sequence reminiscent of gravity assist maneuvers. This is the same technique used by spacecraft to steal momentum from planets and change direction without burning fuel. Yet, every attempt to measure active propulsion on 3Y/ATLAS, whether from jets or hidden engines, returns the same answer. No measurable thrust, no deviation from pure gravitational motion. The velocity changes are consistent with what gravity alone would provide. Citizen astronomers and professional teams have run thousands of synthetic arrivals in orbital models. Nearly all end up with steep inclinations or wide misses. Only a tiny fraction come close to matching the real path of Atlas. The energetic requirements for a natural object to pull off a planetary slingshot, especially at this speed, are immense. Still, the data show no sign of artificial acceleration. The path is precise, the odds are low, but the math holds, at least for now. Observation teams across 3 continents now race the clock. With 3 ESA/ATLAS slipping behind the sun in late October, a blackout in ground-based data stretches for weeks. The next clear window opens in early December, when the object climbs above the horizon for telescopes in Chile, Hawaii, and the Canary Islands. Schedules at the James Webb Space Telescope and the Very Large Telescope are set months in advance, but instrument time is fiercely competitive. JWST's thermal infrared campaign, aiming to pin down the object's surface composition, is tentatively slated for December through January. The VLT and ALMA arrays have reserved slots from December to March, hoping for clear skies and no technical failures. Yet not all data is flowing as planned. During the US federal shutdown in July, NASA's pipeline for high-resolution astrometry and time series spectroscopy stalled. Rumors ripple through online forums, speculating about withheld images and delayed releases. Official statements point to backlog and staff shortages, not secrecy, but the gap in public datasets only adds to the tension. Teams at ESA and independent observatories continue to upload their findings to the Minor Planet Center, but some of the most sensitive measurements, deep spectra, thermal maps, high-cadence light curves, remain pending or embargoed until scheduled releases. With each missed window, the risk grows that critical features will fade from view. The next few months promise a flood of new evidence, or, if weather and technical issues intervene, a silence that could last until 3I Atlas leaves the solar system for good. Avi Loeb, the outspoken Harvard astrophysicist, has never shied from controversy. In a July 2025 interview, he placed the odds that 3I Atlas is not a natural object as high as 40%. Loeb's reasoning draws on Bayesian logic. Each anomaly, from the ecliptic trajectory to the sunward glow, nudges his estimate upward. He points to the statistical odds, less than 0.25% chance for such a precise alignment, and an even slimmer probability for a sequence of planetary flybys. For Loeb, these numbers demand attention, if not outright belief. Across the aisle, planetary scientist Karen Meach and comet specialist David Jewett urge caution. They argue the numbers can mislead, especially when detection biases are ignored. Most surveys are designed to find objects near the ecliptic, so it's no surprise that rare interstellar visitors sometimes appear there. Meach insists that, until direct evidence emerges, radio signals, structured acceleration, engineered surfaces, extraordinary claims should wait. The absence of a tail, or jets, she says, can be explained by natural processes, a crusted-over surface, or dust too fine to resolve. The debate splits into 4 scenarios. First, a dormant comet, stripped of volatiles, drifting in by chance. Second, a sun-baked relic, its activity hidden by geometry or timing. Third, an artifact, a probe or fragment from another civilization, passing through on a deliberate path. Fourth, a data illusion, the product of errors or projection effects. Each scenario has its own diagnostic signals, spectral fingerprints, trajectory deviations, unexpected emissions. The next wave of data, whether from JWST's spectrograph or VLT's adaptive optics, will decide which path the evidence follows. For now, the story remains suspended between possibility and proof. On July 1st, 2025, the ATLAS survey recorded the third confirmed interstellar object, now known as 3I/Atlas. Unlike any comet previously observed, 3I/Atlas shows no tail. Its brightest side faces the Sun, and its path follows the ecliptic plane with an inclination of just 5 degrees, an alignment found in less than 0.2% of known hyperbolic visitors. Despite high-resolution images from ESA and Hubble, no jets or artificial signals have been detected. Multiple datasets remain delayed or unreleased due to operational constraints. Harvard's Avi Loeb estimates a 40% chance it is not a natural object, but most experts urge caution, citing gaps in confirmed data. For now, 3I/Atlas remains an unexplained anomaly. Its presence forces a re-examination of what we expect from interstellar visitors and highlights the limits of current understanding. Until the next release of observational data, 3I/Atlas stands as a silent reminder. The solar system is not as isolated as once believed.